All right then, this is some of Friday's lecture and then also the final video for Unit 3. So we're going to take on a little bit of new stuff regarding term symbols and energy levels of multiple electron atoms here. So as a quick review, the way we define a term symbol is we have a superscript, and that's the spin degeneracy, G of S, and then we have a capital letter which I'm using a script L here to indicate, right? And so G of S is always twice the total spin plus 1, and L indicates the total angular momentum, and we use the capital letters S, P, D, F to see if the total angular momentum is 0, 1, 2, 3, etc. All right? Now, we're adding angular momenta. For all these things, a total angular momentum, whether it's spin angular momentum, orbital angular momentum, or anything, we're adding vectors. And just to remind you, the vector of an angular momentum is essentially the axis of the spinning, of the orientation, of the rotation. So if I have this blue vector pointing off in space somewhere, think of a propeller that's attached to that vector, and the vector is the axle of the propeller, and the rotation is perpendicular in the plane perpendicular to that vector, and the length of the vector indicates how fast we're spinning. So again, that's the way the thing plays out. And since we're adding these vectors together in three-dimensional space, there's all sorts of possibilities, and that's where quantization and m sub z comes to the rescue, because the z components of those angular momenta, resultant vectors, the sum of everything, not the individual ones necessarily, but the sums have to be properly quantized, meaning that they have to come in intervals of h bar, either in even full integer values, 0, 1, 2, 3, 4, etc., or half integer values, 1 half, 3 halves, 5 halves, etc. So either one or the other of those is what's going to hold. And we can talk about sums of angular momenta with only different rotational components. We can talk about sums of angular momenta with only different spins. And then finally, we can take the spin angular momentum and the orbital angular momentum and also add that together. So we do all of that stuff, right? So when we're adding these vectors, there's going to be a big one and a small one. Groß and klein, if I use German, so that I don't get confusing values of these of the names of the vectors. So we're going to use, we have a bigger purple G and a smaller brown K here. And that's the scheme is always figure out the big one and the small one. And then when you add those together, the limits of the possible values go from the G plus K, the sum of the two, as the maximum value you can possibly get, and then G minus K is the minimum value you can possibly get. And that's the range. And typically where people make mistakes here is that they forget that you don't go all the way down to 0 necessarily. So G minus K, if they're not the same size, is not going to be 0. There's going to be a minimum value of this sum. And then the maximum is adding them together, so that's not too terribly difficult. And then the quantization rule is they're separated by units of 1. So we go from G minus K plus 1, etc., all the way to G plus K. And that's the appropriate quantization. It's always times h bar in terms of the z component of the angular momentum. Now, the total number of states here is the product of the spin degeneracy and the orbital angular momentum degeneracy. Twice s plus 1 times twice capital L plus 1. And that's because the spins in the orbital angular momenta have basically nothing to do with each other right now. So if you imagine we have a spin, a single, let's say a P1 configuration. There's a spin, which can be up or down, and then we can be in any one of the 3 p orbitals. So there's 2 spin states, and there's 3 orbital angular momentum states. And I can have any one. In other words, I can have P equals M sub Z equals M sub L equals plus 1, up or down. That's 2 states. I can have M sub L equals 0, up or down. That's 2 more states. And I can have M sub L equals minus 1, up or down. That's 2 more states. So it's 2 plus 2 plus 2 equals 6, or 2 times 3, the 2 degeneracies, equals 6. So there would be 6 possible states in that case. So that gives us the total number of states associated with this term symbol. Now, the reason, then what we can do, and the reason we're adding, we care about the total angular momentum in addition to the L and the S, is because there's this thing called spin-orbit coupling. So when we couple the spin angular momentum and the orbital angular momentum, there's some interesting magnetic interactions that go on that can give us specific energy levels. So we do also want to figure out that vector sum, and we call it J. And J is the total angular momentum of the whole system. And that's L plus S is a vector sum, and so it follows those same vector addition rules that are sitting there just to the left. So there'll be some minimum J plus 1, etc., up to the maximum value of the J value that you can get. So we have this full range of now total angular momenta that we have to play with. Once again, they come in values of h bar. And as I mentioned in class, one thing that I never really got, it just never settled into me when I was a student, was that the amount of angular momentum associated with spin and the amount of angular momentum associated with electronic orbital motion, they're quite equivalent, right? They all come in units of h bar. And so there's just often as much or more angular momentum associated with the electronic spin as there is angular momentum associated with the orbital angular momentum of the electron. Sometimes one's bigger and sometimes the other's bigger, but they really are totally equivalent numbers, and so they both have pretty significant effects on the overall energy. So the reason the spin-orbit coupling exists is because from the perspective of the electron, the proton, it's kind of like pre-Copernican cosmology here. From the point of view of the electron, the proton is moving. So the proton is a positive charge that appears to be in orbit around, in a sort of circular orbit around the electron, if there is angular momentum there. And that is a current, that positive charge. And so that proton, from the point of view of the electron, is generating a magnetic field. So as I've drawn it here, the magnetic field would be in the upward direction. And spins care about that. The electronic spin can orient in a magnetic field. ESR spectroscopy, electron spin spectroscopy, is exactly derived from this effect. So if you make a strong magnetic field, then you're going to orient spins. And in fact, this is why we use the quantum number m for the z component of the angular momentum, because it's called the magnetic quantum number. The way that we figure out what the z direction is usually, if we impose it from the outside, is by putting in a magnetic field whose field lines specify the z direction. In this case, those B lines that I've drawn in gold there, they really indicate the z direction. So that's what drives this thing, and that's why we care about the sum of these values. So in this case, we go from some minimum energy J to some maximum energy J, and which one's minimum and which one's maximum is actually going to depend on the circumstances. So that's the minimum energy to the maximum energy, not necessarily the minimum numerical value of J. So it's J min E going up to J max E, okay? And we'll learn in a second how those get separated out. So from these guys, we can also figure out a total number of states. So each of those spin orbit J angular momenta, like any other angular momentum, is going to have a z component to it. And so there's always twice the angular momentum quantum number plus 1 states associated with something like that. So now it's 2J plus 1. So to figure out the total number of states, we take each of these J values, we compute the degeneracy, 2 times J plus 1, and we add all of those up. So when we're dealing with the S and L values, we take G of S times G of L, and we get a total number of states. When we're dealing with the J values, we figure out the degeneracy G of J for each of the J values, and we add them all up. And the trick is those have to be equal to each other. So these J values are the levels. They're called the spin orbit levels of the system, and they define the energy levels of an individual atom. But we can compare the degeneracy we get from the J, some of the J degeneracies, to the total degeneracy we compare when we multiply the spin and the orbital angular momentum degeneracy, and those have to equal each other, and that's the check that we use for the system. So we compare that to that, and if they agree, we're done. This gives us the ability to populate the entire periodic table using Hund's rules. Now you're well familiar with these rules, so all I want to do here is give you the quantum reasons why these rules actually play out. So the first rule is that we take all of these single electron orbitals and we rank them by not just n, but n and l. So we add the principal quantum number n and the orbital angular momentum quantum number L, and we sort them from the lowest number to the highest number, and that's going to be lowest energy to highest energy. And in the event of ties, the lower n value wins. So we have 1s, 2s, 2p, 3s, 3p, and if we add the n plus L, then we go, let's see, 3p, 4s, 3d. If we take the n plus L sums here, 1s is 1, 2s is 2, 3p, now p adds in, so that's 3, 3s, that's 3, s is 0, so that's 3. So there's a case where the 2p beats the 3s because it is lower n. Then we get 3p, that's 4, and then 4s is also 4, but the 3p was lower energy, so just like 2p, 3s, we have 3p, 4s. And finally, 3D is the one that's kind of left out in the cold there because it, even though it's n equals 3, 3 plus d, which is L equals 2, is 5, and so it's beaten out by the 4s orbital and winds up as the higher energy case. So those are the rules, and you know those rules, but the reason for the rules is the interesting bit. So the reason for the rules is the shielding that we've been talking about. And so the 3D orbital has the electrons all very, very far away from the nucleus, and the 4s orbital, even though its principal quantum number is higher, has those secondary maxima, and it's got a lot of them, and so those secondary maxima include the possibility of having the electron quite close to the nucleus, and in the end, that beats out the fact that the principal quantum number is somewhat higher. And so that ultimately has lower energy when you consider the multiple electron interactions and the electronic shielding associated with that. Now the second rule is that we want to maximize spin, of course. And really what we're doing here is we're getting the electrons in different orbitals. So really the rule is not so much maximize spin, is just put the electrons as far away from each other as you can. In other words, when we have a single subshell, when we have a single set of orbitals, like 2p or the 3d we were talking about, we want to spread those electrons out as much as we can. Now once we have spread those electrons out as much as we can, then the maximizing spin comes from what we've been talking about here, that when we maximize g of s, we're making the spatial exchange anti-symmetric by making the spin exchange wave function as symmetrical as possible. So the reason that wins out, the reason we maximize the spin in the end, is to get that spatial exchange wave function anti-symmetrical and get the electrons avoiding each other automatically at the inner electron distance R12 equals 0, rather than having to have a cusp that has high curvature and high kinetic energy. So maximizing spin is actually all about getting that spatial exchange wave function to be as anti-symmetrical as possible. Now the third rule is that we maximize L. We maximize the orbital angular momentum, and basically once we've maximized the spin and we have the electrons as far apart from one another as possible, then we may as well get the most that we can out of this spin-orbit coupling business. And so that's why in the end we look to get the electrons in the highest possible total angular momentum state, because then you can get the most current basically going on to get the spin-orbit coupling maxed out.